Let's continue with our example of simulating exponential random variables and see if we add a few of them, if central limit theorem seems to be kicking in. So this is what we did. We generated some samples. Here we have 10,000 samples from the exponential distribution with lambda equal to 1, and if we draw the histogram of those 10,000 in this case, it's clearly going to look like the exponential density, and this is one of those distributions that are quite unnormal or non-normal to look at. It has a peak at 0 and then drops monotonically. So let's see if we what happens if we just sum two of these. So and then we'll sum maybe 4 of them, 5 of them, and then 10 of them, and see what the distribution, what the histogram starts looking like. So this would be the code. Let us say let's look at the inner loop, the for loop on j. So we run that n times, and for each j we simulate one exponential, as you can see, and then sum those values. So we sum those n values of exponential deviates, and then we look at the outer loop, which is the for loop on I. So we repeat that n MCT times. So n MCT here, as I already said, is 10,000. So let's see what would happen for different values of n. So what you see here is n equals 1. Let's make n equals 2. So we are summing two exponentials, and we can see some interesting things already. Obviously, since we are not normalizing, the distribution is shifting a little bit to the right. So the mean was 1, now the mean is 2, because we are adding two exponentials each with mean 1. So obviously the distribution has shifted a little to the right. But interestingly, the peak, the quite sharp peak of the single exponential has kind of blunted. Let's do that for 5. So we are summing 5, and importantly, all these these 5 exponentials are all IID. So, and that's clear from the way that we are simulating this. Every time we simulate a rand, it's an independent sample from the uniform distribution. So clearly, when we sum 5 exponentials, the distribution does shift more to the right, but it's becoming more and more kind of rounded, with a central peak and falling off on both sides, although it's a bit more, it's still a bit skewed to the right. But the inevitable nature of the normal is clearly becoming apparent. So now when we do 10, it's looking more and more like the classical bell shape of the normal. Obviously this is no proof, this is very non-rigorous, but if we want to make it a little make it more rigorous, obviously we would do a goodness of fit test, but that is not the purpose of this example. We just wanted to illustrate pictorially, graphically, what happens once we start adding a few independent random variables, and by simulation what the distribution, what the histogram of the sum would look like. And at least graphically it seems that central limit theorem is kicking in pretty early. We don't have to wait for n equals a very large number. Even with 5 or 10, the result, the strength is becoming very clear.